You are welcome once again. We started the discussion 2 days ago on linear regression, and we have gone through the rudiment, the historical background, and some rudiments about it. And I think the last bus stop was here, where we talk about fitting the line, the regression line, that you either use hand or use computer actually does it, but whichever way, the best way is the method of least square. The best line is called line of best fit. That is the line that best fits. Because if you have scattergram like this and you want to draw line, there are many possible lines that can be drawn. Which one is the line of best fit? The line of best fit, we have said, is the one that maximize. Is it maximize now? Minimize, or which, okay. We want to reduce the distance between the line and each point. So the one that is closest, that is averagely that is closest, that the distance between each point and the line is the smallest. And the way we can do that is to square the distance between the line and each point, and now add it together. The reason we have explained why we do that is that all the points above the line, they are positive, the deviation is positive. The one below the line, they are negative. If you add them together, if actually even the line is the best line, you end up the amount of negativity will be equal to the amount of positivity. At the end of the day, what will happen to be zero. And that is why we already explained that, even when we're discussing calculation of variance and standard deviation. So what the intelligent people did was to now square. When you square something that is negative, it will give you positive. So when you square the deviation, both positive value and negative value become positive. So the one, if let's say we draw different line and we do that, the one that is smallest, that have the smallest value will be the line of best fit, because it minimizes the distance. So it's the one that has the least square. When you square all the deviation, the least, that is why they call the method of least square. And we have already discussed that. And we said that when you feed the line, you now have your regression parameters there. The beta, which is the regression coefficient. And we also have the beta 0, beta 1 regression coefficient, beta 0, or A, which is the constant, which is the value of y when x equals to 0. We have discussed that. I want to quickly look at an example, a real example, and work it out, and so look at the value, and now explain something that is very, very important. When before all these things can make meaning, the line, how do you ensure that this regression and the model, the regression plot, the model actually is actually good. It's actually fitting very well, because something you can produce something, may not do it. It may not. The validity may be questionable, and it's just like somebody say decide something to treat or to detect something in the hospital or the setting, and actually the thing that actually doesn't actually detect it. Whatever you saw, you cannot rely on the result. The validity is questionable. So sometimes the validity of regression model may be questionable. We look at how we assess how fit, how valid the regression model is. But before we do that, let's just look at this example. Well, the example itself is just an example. Look at, I think it's the example we also use for the correlation coefficient, which look at the height of children and their pulmonary desk space. I already established the fact that when you are looking at the relationship between height and pulmonary desk space, height will be the independent variable, pulmonary desk space will be the dependent variable. The pulmonary desk space, they cannot determine height, but the height will determine pulmonary desk space. Well, people can say that vice versa, it can. If the pulmonary desk space is much, if the child is not growing very well, maybe there is no perfusion, good perfusion, but we know that it's the height, if you have to consider the two variables, The height will determine the component desk space. In that situation, the height will be the x, which is the independent variable, and the component desk space will be y, which is the dependent variable. And we just put it into the formula we have talked about before. So this one is just about determining. I don't think we should bother ourselves much about how do you determine the correlation formula, regression formula from, the correlation. It's actually from, you can get it from the correlation. So, okay, let's just go through. Change in the, let's just go through for academic purpose. You can start shouting your question. Yeah. No, we want to quickly look at computer. How do you compute regression coefficient? So instead of saying that it's computer that computes it, let's see how we compute. You can compute it. Change in the dependent variable y is measured by covariance of y and x. You see, we talked about covariance the other time. From the covariance we derive, when you divide covariance by the standard deviation of the two variables, it gives you the correlation coefficient. But now we still know that these two variables, x and y, so they are covariance. You know that when we are talking, because our regression, what we are looking at is how does variable y, which is the outcome variable, vary with variable, the other variable. Covariance means that they vary together. Now, but we know that one variable depends on the other. So what we are interested in now is that how does y vary in relation to, as x vary, how does y vary? So to measure the change, if the change in y is due to x, so the only way you can measure is to look at their covariance, how they vary together. Whereas change in the independent variable, which is x, is measured by the variance of x. Can you see that? So how do you measure the change? Because we want to see what we are looking for is change in y due to change in x. That is, as the dependent variable change, independent variable rather change, the y, which is the variable, how does it change? If that is the case, how do you measure the change now? So measuring the change, the variability of independent variable x, is by measuring the variance. Whereas measuring the change in y due to x, then you have to measure the covariance of x and y. So that is just the explanation there. So variance, if you look at, remember, formula for variance for x, it said would be this one, just for you to see, sigma x minus s bar. We remove the s bar from x, square it, and divide by the standard degree of freedom. This is it. That is the variance. Let me bring my pointer.
Where did you take it?
So that is it. Now, if y, somebody is talking, please, everybody be muted. So if variance of y now will be, if you want to measure variance, of course, sigma y minus y bar square, but it's just like the x. But we are not interested in variance of y now. We are of course, you are interested in variance of x. We are interested in change in y by due to change in x, and the only thing that can measure is the covariance of x and y. So covariance of x and y is this. So consider the following: change in x is the variance of x. Change in y is the variance of y. Change in y due to change in x is the covariance of x and y. So regression coefficient B, which is the change in y per unit change in x, now will be, so all you need to do is to divide, is it per unit change in x. So that means that you are dividing covariance by the variance. So can you see that? So covariance of x and y by the variance of x. So if you look at it, this formula is the covariance of x and y, and this one. So when you change the formula, you remember this is division. If you not change it x, the numerator, if you not change it to times, the numerator will become the denominator. Can you see? If you change now, can you see the 2n minus 1, which is the degree of freedom, cancel out. When you cancel out now, what you now have is this. which is formula for the regression. Can you see how correlation and regression are related? The correlation is division of covariance of the two variables by their standard deviation, while regression coefficient is the division of the covariance of the two variables by the variance of x. Can you see? Correlation is division of the covariance of the two variables by the standard deviation of the two variables, while the regression is the division of the covariance of the two variables by the variance of the x, which is the independent variable. So by doing that, that's the formula. So when you are able to get B now, I've already said it before, if you are able to get B, it's very simple for you to get A. A would be, if you calculate the mean of x and y, the mean of the dependent and independent variable, you put it in the formula. The y is equal to A plus bx. So if you change the formula now, you now make A, because you already know the regression. We have already calculated from this formula now. You already know the regression coefficient B is A. You are looking for the constant, and that one is the regression coefficient, is the slope. While you are now looking for the constant, where does the graph cross the y-axis? That is the A. So you now use the formula. You now feed in the x and y, the mean of x and y, you're able to get A. So in that case, when you get A and B, you can plot your graph. So even if you don't even plot graph, you have already gotten the characteristics of the relationship. So all you need to do is that if you bring somebody's height, you can predict from that in the formula, you can predict the combinatorial test space. Now, these are the computing Pearson correlation. Okay, I think I'm just repeating it so that this is how we compute the Pearson correlation coefficient. So I think we have discussed Pearson correlation coefficient before. So I just put in this. Okay. You Pearson correlation coefficient. Yeah, that's it. So we'll move forward. Now, what I want us to do look like now is that. So if you look at what we have just said, so you may look as the most important thing to you would be beta and the constant. Beta and the constant. That is, the beta is the regression coefficient B, and the constant where the graph cross y-axis. But before it can make meaning, there are the graph itself, the model you have built, does it even make sense? Because those are the things that people look at. Me, I've seen what some people do. Even in a university, they were trying to look at the factor that determines student performance or whatever. So, and they did regression. I saw one. I just look at, by the time they fit in, they use linear regression. When I saw the work, and it was showing me a PhD student or a PhD person in the university was showing me, and I now look at the R square, this parameter, and I discovered that the proportion of the change in the y that is even accounted for by y by x is so small that that model said does not even make meaning. What it's telling us is that most of the variables they study in that study they don't even contribute too much. What they contributed was even less than 5%. So you see, I have 95% that are outside their work that are responsible for the student performance. So, and if you just go and just say, you just listed these are the things, you publish that type of work, people who take decision, they just waste their money. They take decision with the thing, maybe expert has spoken, somebody has published it that if you do this, these are the factors responsible. You try to tackle it. You spend money, you draw a program to tackle it, it will not solve the problem. That's just it. Now, let's look at how do we assess the goodness of fit of the model? How do we know if the model is very good? The method, there are two methods. What we call R square and what we call F ratio. You remember when we were discussing ANOVA, we talked about F ratio. F ratio is the statistics of ANOVA. And then you remember I said that ANOVA and regression, they are the same thing. They're actually two faces of the same coin. In those days, the researchers that were interested in experimental research, they use ANOVA a lot because from the inception, from the time they conceive of the study, the design state, they try to control for confounder. And that is why they have many, many groups. They say this one is taking placebo and it's a male. And so it's in this one. This one is placing placebo is a female. You know, this one is placing the active one is a male. This one is a female. This one is black. This one is white. They can even have many groups, up to 12, 8, 6. Because they try to control for the factors they think are confounder from the design. So they now have many groups. So it means so when they are now dealing with quantitative variable outcome now, they have to calculate, compare the mean between 3 groups, 4 groups, 5 groups, 6 groups at the same time. They use ANOVA a lot. Whereas the non-experimental researcher or observational study people, they tend to, you know, they will not, because there are a lot of issues. Most epidemiological studies are observational in the sense that you cannot perform experiment with human beings. So because of that, so experimental design, most of them are observational. So you cannot even control for confounder from the inception. So you have to wait till you do analysis. And that is when you now run regression. But they didn't know that they were actually doing the same thing. So regression and ANOVA are actually the same thing. And it's a matter of time. Even for experimental design, ANOVA will give way for regression because when you run regression, ANOVA is part of what you are running. Look at it. That F ratio, we talk about the variance between and variance within that we discussed the other time. So in F ratio, what it does is to compare the variance that is due to the model between, which you call between, by the variance within that is due to inherent variability. And we have already said that that is the logic behind all hypothesis tests. Variance between over within. That is the basis for all hypothesis tests. So now, let us look at this first statement. The most basic model is the mean. So the most basic model that actually predicts the values of the outcome is the mean. Well, mean for, if it's for quantitative outcome. For qualitative, is the proportion of that thing. No percentage, that's the most basic. So if it is, so when you do, most of the time when in your descriptive statistics, you summarize. For quantitative, you summarize as mean. For categorical, you summarize as percentage. You'll be sure that those mean and percentages you do in your univariate analysis, they are the most basic model. How? Now, the mean assume that everybody is the same. For example, now, if they give maybe 5 of us 1 million to share, you say, how do we share? People just say, 200,000. But you just assume that all of us, all the 5 people are the same. They are the same in rank. That's why you just assume that it will be equal. So the mean, what you just did is to calculate the average. Okay, even if everybody receives different things, by the time we add it together, total is 1 million, and all of us are 5. That is the average amount. So it's an assumption that all of us are the same, and that is why. Because, for example, somebody you have a school now, and maybe your friends so they went to UK, You want to do inter-sport in your school? That's it. Hey, let me buy clothes for my student. And when your friend get to UK, they are asking me, what is the age of your average age of your student, average age of your student in your school? You now call the head teacher and say, how was the average? Average age there is 7. So they now want to shatter everything for 7-year-old person. But the issue is that all of them are not 7-year-old. But that is the average age. So when you now bring the clothes for 7-year-old person, for some it will be too big, for some it will be too small. But there are some, of course, that it just be perfect because it's within that range. So me, what the mistake usually do is to just assume that mean, that's average. Just bring the mean. That is the most basic model. But you discover that most of the time, as you're going to see in the next class, most of the time, you see each value is far, far, far from the mean. The deviation is much. But when you compare that mean as a model, you compare with a regression line, regression as a model, you discover that for regression, it's closer. Let's just look at it. Can you see this diagram now? So the first diagram here, the first box here is looking at, it's the same plot, it's looking at the plot. This first plot is using mean as the model. This second plot is the regression model, just like the one we have shown before, that slope up. Then you can slope down. It's just only that this one is just positive direction. You can slow down, but the issue is slope. There is a slope. So this second one is the regression, while this one is the mean model. What we are saying that this one, the mean of the y, is horizontal if you are plotting, because it doesn't change. It's just the mean of the outcome of the y. If you remember, the y is the exposure, is the outcome, rather x is the exposure. So what you are trying to predict is the y. So if you look at the mean of the y, let's say this value is the mean, it will be horizontal like this. But this is the regression, it goes up, it varies. If you look at these different dot, those are the location of each value. You will see that compare this mean as the model and the regression line as the model. You see that those points, they are closer to the regression line averagely than the mean line. It shows that, yes, the mean is poor in predicting the value of the outcome. But how do we have drawn the regression? How do we know if this regression also has done well? So the only way you can know if the regression, the only possible way is to compare and try to compare the mean as a model and the regression and see how improve. What improvement has the mean, the model brought, the regression model brought in that make it better than the mean. So if let's say that we have the two, maybe we have 2 or 3 regression model now. If you compare with the mean, the one that is far, far better than the mean will be the best among them. That's what it just means. So now, if you remember, we said that along the line, that is the model. But because the line does not perfectly predict, so the distance between the predicted value is where each dot meets the line, while the actual value is where the dot is. So the difference between where the dot is and where it meets the line is the deviation, or we can say the error. Now, in this graph now, the error or the deviation is the distance between each point and the line, because that's where it misses it. But of course, the predicted value for each of the dots is on the line. Now, as we already said before, that for regression, even though they are not all of them are not on the line, but they are closer. The regression line is closer to each point than the mean line. Now, what we now looking at is that, so the difference now is what we call, for the regression line, the difference here is, if you remember, how do you know the deviation is by squaring it, because you do actually the value of the deviation. You cannot add it together because some are negative, some are positive. If you square it, whatever I give you, you add it, that is the sum of square. Sum of the square. So for this regression line now, what we have, the sum of square is the sum of square of the residual or the error. Sum of the square of the error. Whereas for if you come to the main line, what you have now, if you square it, it's the same thing also. Some are above, some are below. If you square it, sum of the square total, because that is the total variation you can see in that is in the data set for that y, for the outcome variable. The total variability is when you look at it, the average, then how each of them differ from the average. So the total variation that can be explained for the y is what the mean as shown as model. Why? That's what we call sum of square total. So when you run your regression, you will see something like sum of square. Sum of square, you see a model, residual, total. So when you have the model, the sum of square model, and that of residual, it gives you the sum of square total. It's easier to conceptualize with well, some people say that this was easier, but I thought the ANOVA one, if you are explaining ANOVA, pure ANOVA, it's easier because we talk about total sum of square, which is the deviation of each value from the grand mean. We also talk about sum of square between which is the deviation of each mean of each group from the grand mean. We now have sum of square within, which is we correspond with common square residual here, which is deviation of each value, the mean of each value from the mean, or deviation of each value from the mean in each group. So in the same thing, we have the sum of square residual, which is correspond with the sum of square within for ANOVA. We have the sum of square total, which correspond with the sum of the total from the grand mean for ANOVA. Then how do we know the sum of square between which is the model? What improvement has the model brought? The improvement the model has brought, if you now overlap these two graphs now, if you overlap, the difference you can see is what it has brought. The difference you can see between the two graphs is improvement the regression has brought to over the mean. So that is the sum of square model. That is the model. So the bigger that one is, of course, you expect the better. So how do we now quantify that improvement it has brought? And the improvement it has brought, two ways to quantify is what I said, R square and F ratio.
Give me time.
In R square, what R square does is there are two ways you can even bring it out, or three ways you can even bring the R square out. You are running it. If you have the correlation between X and Y, if you square the correlation, it gives you. That is why that's where it gets its name from, because you represent the correlation by R. PSC correlation by R. If you look at correlation between X and Y, so of the two variables, if you square it, it gives you that. Then another way that that one alone will not give you the meaning. But this one, another way of doing it is this sum of square model over sum of square residual. That is this sum of square, the improvement over what we have here. Oh no, sorry, that one is F. That one is F. Sorry, the sum of square model over total sum of square, rather. Sorry. The sum of square model over total here. The sum of square model here over the total, that is the R square. So that is what is telling you that this is total. The total is total variability that is in the data set. The sum of square model is the variability that the model has brought, can explain. So how much of what is there can the model explain? So that is you put what the model has said over the total. So that's what we call, it's the same thing as seeing the correlation square. If you express it as percentage, that is what we call coefficient of determination. That is input, that is variability, the variation in the outcome variable that is accounted for by the exposure. Because the total variability that can be explained in concerning y is what we have there. But because the variable you put in as x, which is forming the model, can only explain but not all of them. So the proportion it can explain is the sum of square model over the sum total sum of square. That is the same thing as the R square. That is one. Now, the bigger it is, the better. So if you have something that is 80%, you know it's better than 50%. It's better than 40%. If something is 90%, you know that it's better than 70%. That is right. The second one, which is the F ratio. F ratio, what it just does, you know, this sum of square model is what the model can explain. But this second class sum of square residual is what it cannot explain, because that is the deviation from that model. So you want to see, okay, if what it can explain is far bigger than what it cannot explain, that's what is good. As opposed to where what it can explain is so small compared to what it cannot explain. So the way to know is for you to say, okay, sum of square model, which it can explain, over divided by what it cannot explain. If what it can explain is far bigger than what it cannot explain, because you are made in the numerator, it will be greater than 1. Not only greater than 1, if it's far bigger, it will be far greater than 1 until it reaches R. And I say, no, this is big. That is the F ratio. Can you see that? So you see that the F ratio, that's the F ratio we did in ANOVA. So that is the ANOVA aspect. The F ratio is the ANOVA aspect of the regression, while the R square has nothing to do with ANOVA. But both of them, they measure the goodness of it. The bigger the R square and the F ratio, the better. Can I tell you that the more important among them is the R square? See? Now, somebody was asking if in the last lecture that when you are plotting multiple regression, is this good? You do it when you do the multiple regression, is it good to do the scatter plot? Because most of our this thing, they don't have that three-dimensional graph for us. That's why it doesn't make sense. If it is only one, maybe simple regression, you can show it on the. But this is when you show multiple regression. The more the number, the more the shape. This one now, it has more shape. But if so, it may be hexagonal. No, the shape would be the shape will be changing if the more you put in data set. And let me tell you how would be a good one. How as a statistical package. So many people don't use how because it requires some programming, understanding of some programming language. It's more of command. And as time goes on, if people start picking some of these things, pick SPSS very well, pick starters very well, we can bring in how so that people can understand. So there are other things which I think that I will just rush through, don't need to explain into detail, is the step in running, if you want to run the multiple regression, either you use hierarchical, the step you use, a different way you can do the multiple regression. So you can use the blockwise, what you call a hierarchical entry, or you use first entry. You can use stepwise method. For the hierarchical, you can use stepwise method, whether you start from the back or you start from the front. Starting from the back means that you load everything, you start removing one by one to really see how it improves, or you put the one that you think give the best R square, and by the time you do, you start adding. So all you do is that that R square, when you first of all do simple regression for all the variables involved, the one that give you the best R square, maybe the best percentage, that is telling you, oh, this variable it account for 20%. And now this variable account for 10%. And now this variable account for 6%. But the fact that variable account for 20 doesn't mean that one account for 10%, another one for 25%, another one. It doesn't mean it's not additive. When you add them together, it doesn't mean that it will give you maybe 70%. When you add them together, it will not give you, though it will improve on that, on the highest among them. They cannot, it's not additive because they are all related also. So you see that by you may have some variable, even though it gives you some time. By the time you had it, it doesn't give any improvement, significant improvement. It doesn't even have more than 1, or it doesn't even have 1%. You remove it. So you keep on putting variable that give higher value. So when you have started with variable that give the highest value, you add the one that give the next one, best improvement. If a variable, maybe the first variable you put in give 40%, another one give 20%, another one give 30%. It doesn't mean that the one, if you try, you can try to add the one that give 30%. It may not give you improvement like the one that give you 20%. Just like that. So you may have the one that give 20% and may give more improvement on that 40% than the one that give 30%. So that is the one you have first. So so that is hierarchical. So sometimes you don't have everything together, but from simple regression, motive for linear regression is good to do the stepwise method. So then there are some issues. Okay, I think let me just quickly talk on assumption. That's what the assumption, because some of these stepwise we are talking about, it's not good to just beat around the bush. It is easier with workshop. So though we have done them, we have run them in our workshop. If you subscribe, you see that we have our video workshop where we did multiple regression, all these steps, how we went, we had this one, had that, you get it there. So try to talk that in a lecture, to me, is I don't like talking to like too alpha. I like demonstrating. Now, there are some assumptions in conducting multiple regression. Variable type. All predictor variables must be quantitative or categorical with 2 categories. And the outcome variable must be quantitative, continuous, or unbounded. You know, when you say unbounded, when you have something, you put something on Likert scale, you know that maybe 1 to 5 is not good enough. Even for the fact that it's a number, doesn't mean it's bounded. Because it doesn't give that leeway, decimal, all those ones. It has limit, it's bounded. But when something, there can be any figure. But we know that certain things like age may not be more than 30. It's not bounded because, yes, it's because of the type of age, maybe the people that are around. The issue that if we have somebody that live up to 200 years, yeah, it will be there. Doesn't change anything. So, but there are some things that are bounded. So anything that is bounded, something on the Likert scale is not appropriate as an outcome variable. Rather put that one to realm of logistics. But just know that the quantity, it must be continuous, quantitative, continuous, unbounded. That the outcome, the exposure can be anything. But when the exposure is continuous, no problem. When it is categorical, you have to create a dummy that it will be 2 categories. You have to, if let's say, for example, now you want to feed this something like ethnicity, and maybe we have 4 categories that usually have. Now, in doing that, you cannot, there's no way you can just feed in this thing. What you need to do is to now use one as a, out of the 4 categories, one will be reference. You now create dummy for 3. So which one you use as reference depends on the way your data is. Maybe therefore that attribute we are looking at, the one that have the smallest mean for the category, you can use as maybe you are trying to look at mean expirative, peak expirative expirative rates down, or even the pulmonary death rate we are talking about. We are looking at the ethnicity. A particular ethnic group that have the lowest mean of that thing, you can use that as reference. Why you want to know how many times this other one, how much time this one will be more. So in that situation, you use that one as reference, you now create dummy. You now create dummy, that dummy for each of the other one. So if the dummy, the value of the dummy will be 1 or 0, 1 or 0. What it just means is that if you create, maybe you use maybe others as reference now. That's okay, Yoruba as ethnic group, you know, anywhere. For that, you create a dummy for Yoruba. In that anybody that is Yoruba, then you mark it as 1. The other as 0. The drill mean you now create dummy for Igbo. Anybody that's Igbo, you mark 1. The other is 0. You create dummy for Asafla, and anybody that's Asafla, you mark 1, 0. The implication of that is that for the other group that are others, everything is 0 because it's the reference. So in practice, when we do the practical, watch this, you see the way we actually create the dummy. So non-zero variance, the predictor should have some variance in value. You know what they mean by non-zero variance? There are some, especially when the sample size, or maybe that group, a particular category, there are not many. There are not many. That thing does not vary. The outcome variable does not vary. Maybe there are not many. Maybe it doesn't very much. Maybe there are few of them. All of them have the same value. There's no variance. You cannot use it because the regression you are looking at is about variability. You want to know what variability do we have in the outcome because of variability in exposure. So no perfect collinearity. Somebody raised this issue when we're discussing correlation. Collinearity is when two variables, they correlate perfectly. Perfect. You know, we talk about degree of correlation, a correlation degree of linear association. When it's so strong that it's almost 1 or 1, it means that one can represent the other. That's what it means. If two variables perfectly correlate, you cannot use both of them as when you are doing multiple regression. You can only use one of them. Predictors are uncorrelated with external variable. When predictors are uncorrelated with external variable, maybe there's some, but this one is a very funny one because what it really means that there are some variable you have not included, or the variable that is not in your study, it must not correlate with it. But it's a very funny one because most of the people, that one is violated. Homoskedasticity. I think that one's so important that I put it here. What it just means that what this one just means is that you will remember when we draw the line of regression, you will see, we try to see the distance, the error, the deviation for each one. Look at these two graphs now. You will see that when you draw graph for this first one now, even the almost equidistant, almost of these, you can see the deviation of this thing. The maximum deviation from the line would be equidistant as you are going. But whereas look at this one, look like funnel. You see that the variation, the deviation is widening as the graph is going up. So that what it means that the residual are not equidistant. The variability around the graph for the residual is not constant for this one. That's what's called heteroskedasticity. This one homoskedasticity. It's like when you say homogeneity or variance. Homogeneity or variance, you are talking of the data set itself. How the variance for the maybe 2 group or 3 group you are dealing with, the variance, are they the same? Are they don't differ? That's homogeneity. But when you say homoskedasticity, it means the residual in the regression model, the residual should be equidistant along the model. So other assumption, independent error, normally distributed errors, okay, is still part of this thing. Independence and linearity imply that the mean value of the outcome variable for, okay, we have, anyway, everything is more like repetition. So multicollinearity, okay, let me just stop here because the multicollinearity I have discussed it. So these are the effects of the multicollinearity. That the way you can test if there is multicollinearity. So I think let's stop here because I've gotten to know from time that topic like regression, you don't give too much at the same time. So you have to learn. It's better you get some clue, you understand something. As you are using it, you want to learn further, be able to conceptualize your picture. Yes, somebody, is there any question? I saw a good evening. Okay, somebody said you had. Okay, Somebody said I should start. You didn't send your. You have to chat your. Somebody said I should add him or her. So send your number. You can private chat me the number. I will not put you on the WhatsApp. Send your number. Chat me your number. Okay. Any question? Any question? People are not many today, like day before yesterday. Any question? No question. Is it that it's confusing or is but when there's no question like this, either the whole picture is confusing or it's very easy, it's becoming clearer. Okay, there's no question. Let me just stop there. Somebody say, can you please re-explain F ratio? F ratio. Okay. I was thinking F ratio should not even give us much problem. But what it means is, we said that F ratio is a statistic of ANOVA, analysis of variance, analysis of variance. So what you are actually, when you say a ratio, it means that you are dividing two things of the same unit. Because it's ratio that you get when you divide two things of the same unit. Because unit will cancel unit. So whatever you have is not, it doesn't have unit. So what are the things you are dividing in F ratio? You are dividing variances, two variances. You are dividing two variances. You are comparing variance, one over variance, the other variance. You want to know if one is bigger. And these two variances, one is variance between, which is the model, that is the variability, the difference, the relationship you want to see. Is there any somebody is asking a question about these two variables you are looking at? Is there any association between them? Or the difference I'm seeing, the relation with the difference I'm seeing, is it statistically significant? Is it due to chance? So that aspect of variability that I explained that is the model. Then there's one that is inherent, is in that place what the model cannot explain. That is the variability within. Let me share the slide again, because this concept of ANOVA, we can either use pure ANOVA to explain it, or we use regression. It's still the same thing, a different way. Let me, yeah, you will see in this graph that there are 2, 3 graphs here, so to speak. Actually, there are 2. This first one, this second one, and the third one is an overlap. We try to overlap now, this one, I said that how do you measure variability? You measure variability. What is the measure of variability? Is standard deviation, variance, rate. So here we are talking of variance. Variance now, as measure of variability. Now, how do you measure? Okay, somebody is raising hand. But let me explain. I don't know if the question has to do with what I'm explaining. So let me quickly explain this one to ask your question. Now, if you look at this Venn diagram now, you will see that we use mean. We are trying to see there's a scatter plot here. This is y-axis, this is x-axis. It's the same scatter plot. But instead of putting regression line here, we put the mean of the outcome variable y here. If you want to put the mean, so that's that it's just a straight line like this, horizontal. You can now see how each point differs from the mean. The difference between each point is the deviation. The one above the mean is positive deviation. The one below the mean is negative deviation. When you square both, Whatever you get, you add it together. That is the total variability. Well, for you to measure the variance, if it is variance, when you square it and you now divide by the degree of freedom, it gives you the total variance. But even before you divide it, even by looking at it without dividing by the degree of freedom, you call it sum of square. That is, you square it and sum it, sum of square. That is the total sum of square. And that is representing the total variability that is supposed to be explained in this data set. But that is defined by the mean. But when you do your regression, you will see that the regression line fits better because these values are closer to the line. So now, the regression, that's what has explained some variability, but it cannot explain some. The one it cannot explain is because is what we call residual here. When you square all this one and sum together, that is sum of square residual. So why this first one is telling you the total variability to be explained, this one is showing you the variability that cannot be explained by the model. But we don't know yet the one that can be explained by the model. We only have the one that can be explained through the mean. We also have the one that cannot be explained by the model through the mean, through the model, through the regression line. Now, for you to know it, mathematics, okay, you know what the total variability that are to be explained. You know the one that cannot be explained. So how do you now know the one that has been explained? It's just to remove it now. You remove what cannot be explained from the total. So the one, for you to, by just overlapping this graph now, the difference in the two is the variability that can be explained, which is the sum of square model. Now, the F ratio is what can be explained divided by what cannot be explained. Can you see that? What can be explained, which is the sum of square model, divided by the residual, the one you cannot explain. So if what you are trying to look at is that you expect if that model is good, the part of the model it can explain should be far bigger than what it cannot explain. So how do you know? It's by dividing it. When you now make the one it can explain as the numerator, and now the one that cannot explain by as denominator, if it's really bigger, the numerator should be bigger than the denominator. It should be greater than 1. If it's 1, that shows that what it can explain is the same thing as what it can. So that's what it can explain half, it cannot explain half. It's gambling. It's not useful. It's not a useful model. But even if it is a bad model self, what it can explain will be less than what it cannot explain. What it can explain will be far less than what it can explain. When you divide it, it gives you 0 point something. But if it's a good model, what it can explain, since it's serving as the numerator, will be far bigger than what it can explain. So that is the bigger, the better. That is the F ratio. I don't know if I have explained it now. Yeah, somebody was raising hand, Dr.
Yes, sir, Dr. Yes, sir, Dr. Duru. Thank you very much, sir.
Yeah.
I remember when you were talking about correlations, sir, you talked about the fact that p-value is not important, rather than the, yes. I want to ask whether there's a relevance of p-value in regression, in interpreting regression model.
Yeah, it's relevant, but it's not as important as R, as I've told you, it's not as important as R square. The most important thing here is the R square. Is the R square. The p-value is important because the F ratio is the p-value also that will not tell you if it's significant or not. You examine the F ratio. Then the regression coefficient also, there is p-value for it because it's being tested by t-test. There's p-value for the regression, but the most important thing is the R square. And that's nothing to do with that p-value. Yes, thank you, sir. I tried to download from the site. Is somebody, what is the relationship between linear regression and cover? Yeah, somebody asked a question about ANCOVA. Yeah. ANCOVA is analysis of covariance. So actually, it's just a matter of ANCOVA is a blend of ANOVA and regression. That's just it. It's a blend. So when you marry them together, that is ANCOVA. So in a situation now when we run regression, you say you do linear regression, so that you are performing ANCOVA. You understand me now? So because what you are doing is that I gave a presentation recently in EPC in the pre-training, pre-conference training for Epidemiological Society of Nigeria on predictive epidemiology. I try to differentiate between predictive and etiological. Sometimes in etiological, you want to see, okay, how you are removing confounder. You are pointing, you are focusing on one exposure, one outcome. You want to see how this exposure affects this outcome. Though you collect data about many other variables that will serve as confounder, you want to remove the effect of the confounder. But for predictive, you are not interested in, you just want to what are those, you bring many variables, exposure variable, how do they predict? When you combine them together, how do they predict? So in analysis of covariance, it's more like you are doing predictive when you just bring some variable, you know that there are some variables that will affect. You bring them in, you run them together. So that's just it's a blend. So it's one of the workshops I wanted to do, but because when we did regression, linear regression, we also did what do I call it? Logistic, Poisson, cost proportional hazard. This ANCOVA, MANOVA, and other factor analysis, discriminant analysis were other area we wanted to do better. When I see the performance, when it comes the patronage or even the other one we did, it's not so encouraging. So when people are not even learning the simpler one, why are you calling for the more advanced one? It is when people are conversant, they learn the other one, you want to go further. So it's not encouraging. So that last year was a time that I wanted to cover a lot of the ground, to decipher a lot of things, but the participation is not encouraging. Now, so somebody asked a question here. I joined the training late. Please, sir, can you explain coefficient of determination? Okay, the coefficient of determination. Okay, just like, okay, let me go back to the last thing I explained. That same graph. Why is it not, okay, sorry. Let me go back to the, yeah. So if you look at, I've explained all these things. I said this first one is the variance, total variance to be explained. This one is the variance not explained by the model. This one is the variance explained by the model. We have already said that the F ratio is variance explained by the model divided by the variance not explained by the model. R square, which is the coefficient of determination, is the variance explained by the model over the total variance that need to be explained. It's very simple. So what he is saying is that this variable, outcome variable, there are many things that can make it change. But the regression you have done, the variable, either 1 or 2 or 3 variable that you use as your exposure variable, they are the one that form the model. What contribution did they make? That is, what variation in the outcome variable do they account for? That is the coefficient of determination. You express as percentage. When you divide it, you now express as 100%. Over 100 times 100 over 100. You use as percentage. So what the sum of square model over the total, that's it. The variation that can be explained by the model divided by the total variability that is in the and that total variability is only explained by the mean. That is coefficient of determination. So that's the most important thing, even in the regression, especially linear regression. Is the most important thing. When you run something and you now see that this is 80, what is telling you is that 80%. It means that the variable you are dealing with, your x, either is 1 or 2 or 3, they contribute 80%. What does it mean? That if you can target those variables and go and do something about them, it will solve the problem up to 80%, 90%, 70%. So when you are having something like 60%, then when you are having something like 10%, 20%, you know that, well, go and give all the recommendation. You know that it's just a tip of the iceberg. It's going to solve. So what it's telling you, it doesn't mean that your work is not good. It's telling you that there variable you have stored, those variables you are studying here, they only account for there are some other things in your study that may not. There are something like genetic that maybe you didn't even study that may be responsible for the remaining 80-something% or 90-something% of the variability outside your work. So it gives you brain, not to, and that is why some intelligent people, if you want to review or you don't bother yourself about what people conclusion. What's concerned me about your conclusion of your work? What I mean, I want to see your result. What I see the result, I can make my conclusion myself. Because many people conclude wrongly. And people just go, I thought they found out. And they found that is why this list said that there are 3 kinds of lies. Lies, damn lies, and statistics. So most things that many people publish their lies. Not that they told the lie unknowingly, even ignorantly, they tell the lie. And that's why when you just make you go and spend money to take decision based on their finding, you're just wasting resources. I don't know if I've explained that person understand that now. Dr. Jamiu.
Yes, I'm okay.
Yes. So if there's no other one, I think we can call it today.